And our third and final fellow of today will be Balthasar Grabmayr, who is originally from Vienna and is a first-year postdoc fellow in the Department of Philosophy at the University of Haifa. He'll be asking, is mathematics fundamentally incomplete?
Okay, can I start? Okay. So, hi, my name is Balthasar Grabmayr, and it's really a pleasure to be part of this great event. Okay, so my fascination with logic started with a profound shock. The way I dreamt of science and mathematics is that one day, after hard work, we can eventually devise a theory of everything, or at least a theory which contains every mathematical truth. So you can understand my deep frustration when I learned that in the 1930s, a logician called Kurt Gödel showed that my dream is impossible. That is, there cannot be, for purely logical reasons, a theory which proves every mathematical truth. And in the first part of this talk, I would like to tell you a bit more how Gödel proved his groundbreaking discovery. And then in the second part, I will speak about my own research, in which I argue that in order to fully understand its philosophical consequences, further generalizations of Gödel's theorems are required. Okay, and Gödel's result is fundamentally concerned with the limitations of mathematical proof. So what is a proof? And we start by laying down axioms, which capture basic, undeniable facts about numbers or about geometrical objects. So for example, we may have an axiom which says that the order doesn't matter when we add natural numbers. So for instance, we have x plus y is just the same as y plus x for any numbers x and y. We may have another axiom which says that 0 is the smallest natural number, and so on. And then we have logical rules, which allow us to derive new mathematical statements from these axioms in a certain regimented way, right? So you can think of proofs as complex objects which are built together from these axioms. And as a result, proofs provide us with a rigorous method to explain why mathematical statements about numbers, about geometry, are true with total certainty. And since ancient Greece, it has been the main goal of mathematicians to either prove or disprove each mathematical statement. And so now the outrageous thing Gödel did is to show that this goal is impossible. That means that we can actually come up with a true sentence which we cannot prove. And even worse, Gödel showed that mathematics cannot prove its own consistency. So it's impossible to mathematically establish that there are no contradictions in mathematics. So how did Gödel do that? And let me start by briefly introducing the citizens of the world of mathematics. So we have numbers as the paradigmatic objects of mathematics. We have geometric shapes, some of which will be familiar to you. We have functions and operations, and we have sets of numbers and other mathematical objects. And mathematicians typically study the properties of these objects. So for example, we can formulate and prove the claim that there is no odd number which is divisible by 2. And this is a claim about all the numbers in our mathematical universe. But now Gödel was interested in the following claim. There is no proof which derives a contradiction, such as the equation 0 equals 1. And now this claim is about proofs which we use to explain certain features about mathematical objects, but which are not mathematical objects themselves, right? So as I illustrate in this slide, proofs, at least before the time of Gödel, were not part of the realm of mathematics. And so in order to make his claim precise, Gödel had to come up with a new way of introducing proofs as objects of the world of mathematics. And he did that by producing what we call today a Gödel coding. And roughly you can think of a Gödel coding just as a machine which transforms all kinds of objects, such as apples and bananas, into numbers. And in particular, this machine translates mathematical sentences and proofs into their code numbers, and thereby allowing us to express complex mathematical ideas by single numbers. And while in the 30s, it took a genius like Gödel to come up with such an idea, today, Gödel codings are part of our daily life. And I mean, we just heard a nice talk where this was really a strong feature. And think, for example, of your Word document, which is represented by a long sequence of zeros and ones inside your computer, and where all your edits and copy and paste manipulations correspond to certain number theoretical operations on these binary sequences. And similarly, since now each mathematical statement and proof has its own code number, we can use numbers to speak about proofs and mathematical formulas inside mathematics. So in other words, we can now use mathematics to speak about itself. And Gödel used this method to formulate the following sentence. This sentence is unprovable in purely number theoretical terms. And here we meet Gödel with this sentence, but in Gödel's defense, the handwriting is mine. And in mathematics, sentences are either true or false. Okay, so let me now ask you, let's do a little experiment. If you think this sentence is true, then please give me a thumbs up. And if you think the sentence is false, then please give me a thumbs down. You can either pick the emoticon or you just show your thumb into the camera. Okay, great. I see we have a lot of logicians here. That's excellent. Nice. Okay, you're all very clever. Great. So let's check. If the sentence is false, then it must be provable, right? Because the sentence says of itself that it is unprovable. So if it's false, then it must be provable. But now every provable sentence is true. That's the way we set up our proof system. So if the sentence is false, then it must be true. So it cannot be false. Therefore, the sentence must be true. Now, since the sentence is true, it's unprovable, right? That's exactly what it says about itself. And therefore, we have constructed a true but unprovable sentence in number theory. And what Gödel did is he showed that we can come up with a similar sentence for any given consistent set of axioms. So in other words, there cannot be a complete system for mathematics. And this result rocked the foundations of mathematics and shattered the dreams of generations of mathematicians who hoped that one day every mathematical sentence can be either proved or disproved. And while the mathematical correctness of Gödel's result was immediately accepted by his peers, its philosophical consequences remain an open and much debated topic in the philosophy of mathematics to date. So does Gödel's result really show that mathematics is fundamentally incomplete? And can mathematics really not prove its own consistency? And at this point, my research enters. And basically, I argue that even the most general versions of Gödel's result, which are known in the literature to date, are not sufficient to settle these questions. And the reason for that is that Gödel's coding apparatus really depends on a lot of technical and arbitrary design choices, while there are infinitely many equally adequate alternatives to choose from, right? So we have here, for instance, different Gödel machines, and they all translate the very same proof to different numbers. So I argue that only if we can prove that Gödel's result does not fail if we tweak some buttons and screws in his machine, or if we come up with an entirely new blueprint of such a machine. In other words, if we employ a different Gödel coding, only then can we really conclude that mathematics is incomplete. So in order to justify our philosophical consequence that mathematics is incomplete, we have to prove that Gödel's theorem holds for all Gödel codings. But now we are faced with a similar challenge as before, and that is that Gödel codings are not mathematical objects. So here the challenge is to use mathematics not only to speak about numbers and geometrical objects and about mathematical statements and proofs, but also to use mathematics to speak about Gödel codings which translate these proofs into numbers. And in order to overcome this challenge, I developed a theory of Gödel codings by using tools from mathematics, from computer science, but also from philosophy. And then using this theory, I managed to show that we can actually indeed prove that Gödel's theorem holds for all Gödel codings. And thereby we can defend Gödel's claim, namely that mathematics is fundamentally incomplete. And then I soon realized that we can use this theory of Gödel codings to also study the limitations of our computational models and our mathematical languages. So we can study what are the limits of what we can calculate using a computer, given infinitely many time and space, and what kind of are the limits of what kind of concepts and ideas we can express using our mathematical languages. And in doing so, I hope to contribute a better understanding of the nature of mathematics and its ability to model reality. Thank you very much.
Thank you. If anyone has any questions, please ask.
May I ask a question?
Please go ahead.
Thank you, Balthasar, for this presentation. In fact, I was always wondering about this Gödel's theorem, and but you know, very often people provide some kind of self-referenced sentences to demonstrate the incompleteness of mathematical logic, like you said, like the phrase, this phrase is wrong, this phrase is improvable, and so on. But and using these sentences, probably people distribute this mathematical incompleteness to all kind of logic. Like we can't prove that there are twin prime numbers at large scales, but can you comment somehow if whether really the mathematical logic is broken only at self-referenced sentences or not only?
I think that's a brilliant observation. So basically what you're saying is that, and you observed that very accurately, right? Like we have this self-referential construction which are presented to you when we looked at the sentence, this sentence is unprovable. And you're also right that basically in mathematical logic, we self-reference occurs on all kind of levels. And the first challenge is to capture self-reference in a rigorous way in number theory. And I think that can be done very nicely. And there's like a nice theory about it. But now your worry is, well, are there any like mathematical sentences which are free of self-reference? Maybe are there any mathematical sentences which are really to the concern of mainstream mathematicians? And I think, so basically this was a question which was interesting to lots of mathematicians after Gödel's discovery, and there's been a lot of research in that. And the question is now independent of what theory, right? So like here I looked at number theory, and it's still an open question, for instance, if we can actually like formalize Wild's proof of Fermat's last theorem in number theory, right? Like that's still open. But now if we zoom out and we look at really the foundational theory of mathematics, which is set theory, then yes, there are mathematical statements which are shown to be independent of that theory. So we have, for instance, in topology, there are certain claims that certain topological spaces are metricizable, right? And they can be shown, for instance, to be independent of the current theory of sets. But they are free of self-reference, and they are really of concern to topologists, and they are not in funny business of doing self-reference. So I hope that answered your question.
Okay, thanks. I haven't understood, but we can, I guess, continue further.
Okay, the short answer, yes, there are sentences which are free of self-reference.
Thank you.
Nachman has a question. We can hear you, Nachman. You're on mute. Nachman?
No, you hear me now?
Yeah.
I was muted, so my apologies. It's more like a different language. All right. I come from social sciences, so my understanding of Gödel was that you cannot really explain the complexities of a system from the complexities of this own system. For example, you can't use language to understand the reality of language, but there is a hidden subject here, and that's the secret word is truth. I mean, what is true and what is false? And I was curious if it's possible, or if you would like to try to use a different language in two different theories. The immediate association was to Plato's cave, which also implies that you cannot really know what's beyond the cave. You can only see shadows and things like that. And the other theory is much more modern. That's construction theory, specifically I'd say the contextual construction theory, which also deals with this issue. And I wonder if you see any connections between these two perceptions and Gödel's theory.
Nice, thank you. So I do see connections. And so you mentioned truth, and I think that's fundamental. In the end, I alluded to limitations of languages, and we can drop the mathematical at this point. Let's say somehow regimented languages, and as you correctly pointed out, then there is a sibling of Gödel's result, which shows that these languages, basically, we cannot formulate truth or like a truth concept in these languages, and that really, together with Gödel's theorem, really influenced a lot of philosophical discussions. And I think that the 2 points you raised might be relevant here. So I mean, that was of course a huge issue for semantics. How can we like build like a theory of language if we always lack a truth predicate? And then there are all kind of philosophical answers to it, right? We can use like a contextualist approach, or we can maybe just always like go to a new richer language which contains the truth predicate. They're all kind of philosophical maneuvers which can be seen as an answer to these logical results.
Okay, thank you.
So when you show the proofs, in the proof you're searching for a simple answer, true or false, and then you showed that the proofs are consisting of these building blocks, axioms, and some axioms they are true and false in the same time, right? So I wonder, how do you approach that? If you just construct all possible trajectories, so you have axiom A, which is, let's say, is true always, then you have axiom B, which can be true or false, and do you construct this whole tree of all possible outcomes for your final proof? Do you have like some quality measure of like, this statement is for 70% times true, or something like this? Do you classify proofs on a basis of their axioms? How often the final sentence can be true?
Okay, nice. So you caught me cheating there. So yes, we speak about probability relative to a certain set of axioms. So that's actually really important. I pretended that there was something like absolute probability here, but actually what I meant is probability given a certain set of axioms. And now, of course, but what I try to convey is that we can have this like Gödelian phenomenon of incompleteness that can occur, however, like whatever axioms we start with, as long as they're consistent, right? So I don't look, like when I presented the result, I don't look at all possible proofs. I only look at those proofs which can be derived from a certain given set of axioms. And by the way, it doesn't actually matter that these axioms are true. All we require is that they are consistent. So we can actually get rid of the notion of truth from Gödel's result.
Thank you.
Menachem, please.
Talking about talking about incompleteness,
is not always performed with reference to the self-reference paradoxes. But since that has been raised, and since Nachman has broadened the discussion to the ability of a language to examine itself, I think the ultimate problem, to my mind at least, of self-reference is one's ability to be rational towards one's norms of criticism themselves. I mean, if to be rational is to take a critical attitude towards something, there's no way in which you can take a critical attitude towards the norms by which you actually criticize. That's the kind of glass ceiling of the framework dependency theories of science, where truth is of course framework dependent as well. Now, the only way out of that, which to my mind, is that the echo chamber of entering dialogue with people who think differently enables you to create a kind of self-distance from yourself. There's a destabilizing element there, which you can't do to yourself. Like, you can't tell yourself a joke. But someone else can actually do. Is there now? So my question would be, so that this isn't merely a comment, my question would be, since mathematical logic is an observation on systems and the limit of systems, and not of human speakers and human reasoners, is there any way to open the discussion of incompleteness or self-reference in your terms to a sort of dialogical context of being challenged by another system, rather than you know, remaining within the confines of the system you're talking about?
Okay, thanks, and really good to see you, Menachem. So basically, there are perhaps 2 points. The first point is to deal with the phenomenon of incompleteness by basically like looking at the interaction of different systems simultaneously, and I think this can be done very nicely, and there's a lot of understanding in mathematical logic how these systems interact, also regarding incompleteness. The other point is, how can we transfer these results, which you correctly point out are all about formal, I would actually add formal systems, to, for instance, human reasoning, questions about the human mind. And I think there we should be much more careful. So people have drawn quite bold conclusions, and not often really then made maybe their assumptions explicit. So because of course we then have quite heavy assumptions how our reasoning works, how our mind works. And I think for the sake of intellectual honesty, it's important to really keep the assumptions very explicit. And then maybe the results are sometimes less appealing as they sound like when they're formulated by a slogan. But I think it's interesting, and I think we can learn from these results. But I think we have to do philosophy very carefully there. And this has not always been done like that.
I think our time is up, and we have a break. We are welcome to stay here and ask more questions, I guess. But officially, we're on a break until at 12:45, right, Felix? Correct? Okay. So thanks a lot for the interesting talk. And we'll see you guys at 12:45 at the next session.